Hi, my name is Sean Zhao, and today I'll be presenting my work in collaboration with Brian Brubach and R. von Srinivasan on the effects of measuring and constraining partisan gerrymandering on voter incentives. So, an overview of my talk. First, I will introduce some background related to the problem. Then I will go into further detail and establish some definitions. I will talk about how we designed our model and heuristic and how we expanded it for certain experiments. I will then talk about how we applied our heuristic and our model to some real election data. I will further go into detail about how our model and heuristic can be used to answer some questions related to the Supreme Court case Rucho versus Common Cause. And finally, I will end with some conclusions and recommendations. So, just so that everyone's on the same page, partisan gerrymandering is the process where political parties draw electoral maps to manipulate election outcomes so that they can gain an advantage. And computers have become crucial to this process. Specifically, governments can use computers to gerrymandering or to create gerrymandered districts, and independent commissions or third parties can use computers to propose fair algorithms so that they can draw fair districts. And at the heart of all these approaches is the fact that we need metrics by which to establish whether a district is gerrymandered or not. So some constraints that districts must all follow is first population balance, that within a state the districts must all be within relatively the same level of population. Contiguity, the districts must be connected and one district cannot consist of multiple separated entities. Whole freeness, one district cannot be entirely within the other. And then compactness and community preservation. So we don't like districts that, let's say, draw on only a portion of many different groups. Instead, we want most of those districts look like the long lines that you may see as like stereotypically gerrymandered districts. Instead, we want to preserve communities that like are the same livelihood, that tend to follow the same priorities, and so the compactness and community preservation tend to go hand in hand. So the measurements of partisan gerrymandering right now include proportionality, that the proportion of seats won by each party on a district map must be within some threshold of the proportion of the actual population. Compactness and clustering, which I talked about earlier, is the fact that it is like an area to perimeter ratio that we want all districts to follow. The efficiency gap, which was proposed a few years ago, where we want to minimize the amounts of wasted votes, where a wasted vote is a vote that in a district that is already won above 50%. And finally, the metric that we will be focusing on, outlier maps. So the outlier map is now the most prominent legal metric adopted in the legal system. Not only was it used in the Supreme Court case Rucho versus Common Cause, but it was also used in Pennsylvania and North Carolina in court cases that respectively told their state commissions to redraw districts based on this metric. And so how it works is we take a set of voter preferences, which is how voters are distributed across a state based on their party alignment, and we get a distribution of seat counts, which is on a map how many seats will be won by each party, based on a sampling of legal maps generated using a Markov chain. And how we do this is we take base districting, and on that map we tweak it a little, such as moving one census block from one district to another, and through a million or a billion of these steps we create a lot of maps, a lot of different maps, and then we look at the distribution of seat counts based on all those different maps. And then finally we compare the map that we're looking at, that seat count, to the distribution to determine if the map that we're looking at is gerrymandered and is an outlier. And so, as you can see here, in a case study of North Carolina done by Hirschlag, they found that the number of Democrats elected was 4 and 3 in 2012 and 2016 respectively, when on a random sampling it is extremely unlikely that those seat counts would happen. So they established that those maps were an outlier and therefore gerrymandered. And so on a more formal level, we can say that if the fraction of maps awarding seats to a party is less than some threshold tau, where that is the fraction of seat counts, then we can call that map an outlier, and an outlier map is gerrymandered. And so some motivations behind our project is that the outlier metric is popular, but the downstream effects are currently not well understood. So we hypothesize that voters can be incentivized to vote untruthfully. And so to show this, we design a heuristic to circumvent the metric, and then we evaluate the heuristic based on a set of voter preferences to analyze the metric's shortfalls. So we model the process of voting as a simple game. We start with two parties, red and blue, and assume without loss of generality that red is the majority party. And we establish voters that are points on a grid graph, and that districts are non-overlapping polyominoes. And finally, we say that the set of true preferences of the voters, which is their party alignment, and are known to both parties at the start of the game. And so the game proceeds in 4 rounds. We assume that the red party has the majority, so they can draw the map in the first round subject to the outlier metric. And this these voter preferences used for the outlier metrics are based on what happened before this election. And in the second round, voters can vote simultaneously and collude. And in the third round, based on the results of the second round, the majority party can redraw its districts subject to the same outlier metric, but this time the voter preferences used is the voting history that happened in round 2. And finally, voters can vote again, and then seats are recounted. We place some restrictions on our model to simplify our analysis of collusion. We assume that both parties have perfect control and coordination of their voters, though we know that this is not the case in the US legal system. Voters must vote for one of the two parties and cannot abstain. Utility of a party is linear, as a linear function of seat count, where we know that this might also not be true because it might be more worth it to get to 2/3 specifically, or some supermajority, because those can override certain functions of the legislature. We use an odd number of districts with an odd number of voters per district so that there are no ties within the district and no ties on the state as a whole. And finally, we simplify it so that there is a single election between redistrictings, although we know that a census in the US happens every 10 years, and multiple elections happen between those redistricting rounds. So as an example, let's say the voter preference on our quote-unquote state is such that there are 3 blue voters situated toward the top of the state and 6 red voters situated toward the bottom of the state. And since the red party is the majority, it has the power to draw what map it wants. And by inspection, the map that it wants is this one, the one where it wins all 3 seats. However, if we look at all the maps possible that the red party could draw, only the first one gives them all 3 seats. And so that means that the first one is an outlier in our case. The rest of the maps only give the red party 2 seats. So the red party cannot draw the map that it wants. So instead, it draws any other map since 2 seats is not an outlier for the red party. After that, in the next round of voting, it tells one of its voters, specifically the one with B star right now, to falsely vote blue, so that it gives the appearance that the middle column, when redrawn as a map, gives the blue party that district, and so it is still a 2 red, 1 blue map. However, in the next round, the red voter can now flip back to his true preference, and now the red party has successfully engineered a way to win all 3 seats when it was in violation of the metric before. And if we look at all the possible maps that the red party could draw, there is a way for the red party to do that on every single map, such that the blue party cannot follow a same line of thought and counter strategize. So we use our 3x3 model cases to motivate some conditions sufficient for strategizing. More detailed conditions can be found in our paper, but here I will just boil it down to 2 things. There exists some set of target maps that awards the majority party the most possible seats. such as like 3 seats for the red party before, but it cannot be initially selected due to being an outlier. And second, that the arrangement of voter preferences on that map, on the map that the party currently drew, must be such that the majority party can successfully create what we call shield voters, which is this fake blue voter that we saw before, and use them to strategize to achieve the ability to draw the target maps. And so our heuristic is focused on devising pure strategies where the red party can strategize, but no matter what the blue party does, it cannot counter strategize successfully and cannot prevent the red party from achieving the map that it wants. And so with that in mind, for each set of preferences, we test whether our heuristic can find a strategy to gain more total seats than could be gained through just voting truthfully. Basically, we establish that our heuristic is needed as opposed to just voting truthfully. And we implement this heuristic as a global search. And we upped our testing from 3x3 grids to 5x5 grids because instead of 10 valid district maps, there are now 4,006. And we consider all the possible preferences of 15 red and 10 blue voters, as that is, we call that somewhat of a majority, but it's also somewhat of a close party split. And the first thing we had to do was, of course, establish the outlier threshold for the outlier metric. And based on running some tests and these graphs, we established 2% as a valid threshold because it bans a considerable amount of 5-party seats that the red party could just draw firsthand without having to block off many 4-party seats that they could win, as 4 is the most common number of seats that the red party could win in an initial map. And running a heuristic on all of these preference sets and districtings gives us that the first number below each bar is the number that the number of seats that the red party could achieve by voting, the maximum number that the red party could achieve by voting truthfully, and the second number is the maximum seat count that they could achieve by using our heuristic to strategize. And while in some cases the red party does not gain any seats through our strategizing, such as 4 to 4 or 5 to 5, in almost half of all cases, the red party can use our heuristic to strategize and go from a 4-seat map to a 5-seat map that was initially illegal, but due to strategizing is now legal. And we expand this to a case study of North Carolina, which is one of the most notoriously gerrymandered states. Despite a close 50-50 party split, Republicans controlled 10 out of the 13 House seats. And what was launched it into prominence was that it was the main subject of the Rucho versus Common Cause Supreme Court gerrymandering case. And what is helpful to us is that there was a beyond gerrymandering project called together a commission of bipartisan judges to create what is called a judges map that was meant to correct the 2012 and 2016 maps and be more fair. And we modify our model and some of our conditions. We retain our banning outliers, our 2-party system, and our 4-stage game cycle that we used in our previous examples. However, instead of single voters, we use voter tabulation districts, which are basically sub-blocks of census blocks, which is encoded with the number of Democrats and Republican votes per area per district. And now we instead of linking individual voters into polyominoes, we create districts by linking voter tabulation districts into subgraphs of the state. And we will redefine the shill voters to encompass the whole VTD and not just individual voters, of course. In our modified heuristic, we use shills as close to districts of the majority party that they lost initially as possible. To use them to flip and by proximity, we can win back the district that the red party lost, so that it can draw a map that gives them illegally 10 seats. And through our results, we obtain a new distribution of seat counts where 10 seats is not an outlier and therefore we established that Republicans can pick a 9-seat map, which is legal, strategize, and then pick the 10-seat map, which was illegal, but now through some strategizing is no longer illegal and can be legally drawn. Now we will investigate some questions related to the Rucha versus Common Cause case that our heuristic could use to tackle. One is the proportionality rule, which is the fact that which I talked about earlier and has been explicitly struck down by the Supreme Court as a valid method of determining gerrymandering. And while there are some questions that were raised of whether the outlier detection method actually just enforces proportionality, we can see here that the outlier metric is not at all like really correlated with proportionality, and in some cases just outright bans those proportional maps. Another question that was raised was the notion of individual harm, which is that does a individual's vote diluted by a map based on their political preference? And we introduce a hypothetical test using our model that for a given individual, what happens if most maps place them in a district where their party wins, but the proposed map does not? And we specifically use a 13-12 split, where 64% of the time, any of the 13 majority voters would be placed in a district of their party. But because there is no single map that does that to all the individuals, this individual harm, we cannot really use this test as an individual harm test. So in conclusion, we show that careful scrutiny should be given to any measurement which uses past voter behavior, as it can be falsified. Some further steps that we could use to improve this model is a more realistic model for influencing voters, not, let's say, perfect control, but something related to the election security or election tampering issues going on. We could add noise or change the number of voting rounds to make the model more complex. We could use more sophisticated algorithms and computation to raise how much we can investigate. And finally, I would like to say that while this talk has been mostly talking about the shortfalls of the outlier metric, we can also consider how gerrymandering metrics that use past voter data can be less susceptible to strategizing, and use that to further build on these topics. Finally, some acknowledgements. Our team would like to thank Jonathan Mattingly from Duke and Alan Freeves from Carnegie Mellon for their extensive guidance in some aspects of this project, and for ACM EC 2020 for allowing us to present our work. Thank you.